Now let's take a look at alphabetic writing. With an alphabet that spells words, we have a lot more flexibility than a language or a signaling mechanism like Paul Revere used, where a given signal represented a whole thing, a whole message, or a whole object. With an alphabetic language, all we need to do is to have a unique pattern to represent each letter, and we can then transmit one letter after another and spell any number of words or any message. So this is actually much more economical in terms of the number of patterns we need, and it's much more flexible and powerful than a pictographic representation of information. Now here we have an example of something familiar to Christians. It's the Lord's Prayer, Our Father who art in heaven, as it's translated in English. Here we have it, just for variety, represented in Greek. Greek is a language that also has letters, and those letters can be used to spell words. We can decide how many bits we need to encode a message in Greek by thinking about how many different letters we have to be able to represent. Well, in fact, we don't design a different scheme for every language. Some languages have 26 letters, as we have in the English language. Some languages have fewer letters, and some languages have more. But we have standardized so that everybody can use the same computers and the same memory and the same circuitry, 8 bits to represent a character. And you know from what you learned earlier that with 8 bits, each of which can be in one of two states, that is on or off, we have the possibility of 2 times itself 8 times, or 2 to the 8th power, different bit patterns. That turns out to be 256 different bit patterns. They're not numbered from 1 to 256, however. They're numbered from 0 to 255. Here we have a message in Greek. In Greek, it reads as this: Pateriman oendis oranis. And that's what that means as pronounced in Greek. So we can use our 8 bits to represent each one of those characters, and we could store this message, but not in ASCII, because in ASCII the 8 bits represent the letters that we use in English. A different meaning associated with those bit patterns would be necessary for Greek, but we're not worried about representing things in Greek in this course. English is good enough for us. Here's, just for example purposes, another language. This is the Cyrillic alphabet, in which Russian is written, and it has 33 characters. It could easily be accommodated with the same 8-bit bytes. Now here's something to turn things around on you to think about. We've figured out how many bit patterns we could have if we have a given number of bits. But let's suppose we wanted to represent Chinese, and the kind of Chinese vocabulary that's useful for technical purposes, which is 6,000 different characters. Here's the question: what's the minimum number of bits that we would have to use to be able to represent 6,000 different characters? In other words, to get 6,000 unique bit patterns, how many bits would we need to use? Think about it and figure that one out.